Hi guys, welcome back to the Astro Imaging channel. Tonight's session is full frame guiding and focusing presented by Gaston Baudat from Innovations Foresight. But before we go into that, what I'm going to do is I'm going to quickly show off our image of the week. This week we have a really nice one. M81 and M82 and its surrounding IFN by Jeff Weiss. This is a great image and definitely deserves a shout out. I really love this region, and showing the IFN in it is just awesome. We've actually had two winners of the image of the week recently, one on M81, one on M82, and seeing it this way, more wide field, but going a lot deeper, just really is really impressive. And I do want to remind y'all, you can go right onto our website and submit your images right there, and you'll be in consideration for the image of the week. We can definitely use some more images on there, so check that out. And while I'm taking back my screen, I do want to remind everybody that we do not monitor the YouTube chat. We have our own chat on our website, theastroimagingchannel.com. So if you go there, you can both watch the video and get in on the conversation, ask Gaston all of your questions, and that's probably the best way to do it. All that said, I'm going to hand it over to Gaston, and we are good to go.
Well, thank you, Adam. I'm going to share my screen. What I'm going to do is a presentation in two steps. One is a slideshow and then a live demonstration, if I can say so, with a bench. So let's share the screen, and you tell me if you see my screen. Do you?
Yes, I do.
Okay, I'll start with the presentation first, the slideshow. So the full frame guiding and focusing, it's a project and technology I was working on. I've been working on since several years and filed a patent and work now on a prototype software which work on Windows with MaximDL, which is not a limitation. Eventually will work on many platforms, but already had a lot of tools using MaximDL, so is why I started that way. But before I go in more detail about the idea, which is close to what Bob presentations was a bit more than a month ago, let me give a short refresh on the enabler of that, which is the on-axis guider, because I'm not sure every viewer have seen or heard about this, and then we move on the full frame guiding and focusing itself. So the on-axis guider is a system designed to guide on axis, right, using the infrared light from the target, or a guide star in that case. So you have some start lights coming from a guide star usually, but you will see we can do more than just a guide star. And you have an on-axis guider which is made with a dichroic beam splitter. So the beam splitter is not dividing by, the energy of the beam, but is splitting the energy, the wavelengths. So you have the visible and near infrared lights coming from the, let's say, the guide star on the scope side. And then you have the visible up to 750 nanometer going toward the imaging camera, which gives you access to the full visible band plus the H-alpha. And everything above 750 is sent to the guiding camera to do guiding and focusing. And I'm going back on those aspects a bit later. Okay, now you see here the process. The light comes here, infrared and visible. The visible is reflected, therefore there is no aberration. And the infrared light goes through and seen by the guider. Our product have a stage on the back with a helical focuser for the guider. With a stage you can move the guiding camera roughly across a field of view, which is like a full frame. Especially useful with small cameras, but we can also, without moving the stage, support cameras with chips up to 28mm in diagonal, pretty much APS-C size. And that's why I think is an enabler on what you're going to see now. So let's talk about the key features of this full frame. The idea is to use the on-axis guider capability wide field of view at once, which means we have a very large field of view, 28 millimeter in diagonal, without moving anything. And you are on axis, so you can even guide on the target. You will see it could be useful in some application. So today there are more and more low-cost, large ship, like APS-C size or close camera, monochrome. Among them, you can see the ZWO. They have been quite aggressive on the market with the price and very good product. We used to have a lot of customer going remote and robotic. And what they did is, because they don't want and they can move the stage, they buy large monochrome camera, but they used to be expensive, a few $1,000, because those camera was designed for imaging. Now with this lower cost, good camera, CMOS technique, you have something very close to the price of a good guider with a very large field of view at once. So that means now we can process the whole guide frame. We don't truly need to look at the guide stars. And actually, we don't want to make any assumption about what we are looking at in terms of image. We're going to make some assumption about the noise, but not about the image. That's the whole idea. So try to process everything which is in the frame. We can do this way guiding and focusing when you use an ONAG under very low SNR. You will see that through the demonstration on the bench. Also, because you process the whole frame, you can significantly decrease the seeing effect on guiding. And for those who saw my presentation on this astro imaging channel on seeing, you would understand why. I'm going to say a few words, but not much, because it's not the goal here to talk about seeing. But it's one of the interesting capability of going full frame. And of course, as I said before, is ideal for remote and robotic operations, because you don't have anything moving. It's a solid state solution. So the idea behind full frame, and I'm going to start with first guiding, and then I go next to the process of focusing in real time. The idea behind full frame is to look at some type of image registration between a reference image you took once and new image coming, every few seconds or whatever from the guiding camera. So you want to retrieve some dx, dy image registration values from the whole frame. And you don't need to assume anything, and you don't want to assume anything about the image itself. So now I'm going to show you an example from a space image who has nothing to do with a deep space, or there is no star, but it's still, a moon landing is still related to space. And here I took this image, and what I did is I crop it and offset it by roughly 100 pixels. And you see two people on the moon, with a flag and a spaceship on the back and a landscape. Well, if you use image registration, typical techniques like digital image correlation, you can actually retrieve information about the registration error between those images. And even with some type of processing, you can also retrieve rotation information. So below, I'm going to show you two images of the correlation function in a 2D and 3D color plots. So the 2D plots shows you the level of correlation, and I think do you see my cursor moving?
Yes, we do.
Okay, so I have a dx and dy here, and basically this is an image made of the two images, the reference and the new one, and this is all the possible range of registration. And this image has a maximum, which is in red, 1, normalized to 1, at which the two images are perfectly registered. And I told you they are roughly offset by 100 by 100. So that means if you look here, you in 3D, the same image, you see a peak over here, which is where the correlation between the first and the second image you saw on the slide before is maximum. So we can retrieve this information processing those two images without knowing anything about the actual content of the image. It could be your dog, your car, your house, a moon landing, or an astronomical image, anything. Basically, it's very close to the concept described by Bob. image guiding. It's a bit different but close. So when you have a good SNR, that's a key aspect, and have 1 star, and I'm going to take the seeing out of the equation for the time being, it's pretty easy to use the same technique for guiding. So here I'm going to show you a raw image from a guider with a good SNR. And I'm an engineer, I use SNR in dB, but 20 dB is a factor 10, right? And there's 1 star, no seeing, and in all the calculation you're going to see, all the presentation, I use a dx dy of 30 pixels, just to make it simple. So that's the registration error between the 2 images. So this is my first image, my reference one, with obviously a guide star. There's only 1 star and just noise. And you see the same one moved by 30 pixels in X and Y. So if you apply the correlation technique you saw before, that's what you get on those images. Same thing, 2D and 3D plots. 20 dB, good SNR. You see the plot on the left with a maximum, obviously around 30-30, as you would expect. And you see a peak here. So the peak is a bit noisy, but we can clearly see it. And with some low-pass filtering, you can extract the peak. It's just a matter of filtering the noise from the signal here. That's okay, but the problem in our application is sometimes you don't have 20 dB SNR with a very nice star available out there. Depending of the exposure time you may have on your guider, or just where you are looking at on the sky. So you want to be able to do the same with a poor SNR. And this is an example, the same ID with 1 star, still no seeing, so everything is perfect except it's noisy. The raw image with 0 dB, so that means the level of energy from the power of the star is pretty much the same as the noise floor. Same dx dy, so you can barely see the star over here, right? You can guess because you know, but it's pretty much on the noise floor. And this is the same thing with an offset of 30 by 30 on X and Y. Now, if you apply the same correlation technique, you get this pretty much, you don't see anything because of noise. I mean, you have to understand, you have a sea of noise and few pixels of information. And that's a challenge with astronomical images. Unlike the moon landing, you have a lot of information in the moon landing, a lot of patterns out there. There's still noise, but there are a lot of information available for the calculation. Here you have just a very tiny amount of pixels at the level of the noise floor, and you don't get much information to retrieve this. No, you could say, okay, there is no peak, there is nothing to do. We are just, stuck. Well, it turns out, though, although you don't know anything about the image itself, and I don't want to assume anything anyway, I may do some assumption, and I can do some assumption about the noise. So my background, among things, and my PhD is in statistics and machine learning, and there are techniques out there to modelize the noise and do some type of optimal filtering. I'm not going to jump on the detail on the mathematics either. I don't think it's the goal here of the presentation. And also part of it, from a company point of view, would be a trade secret. My wife tells me it's great to have a passion for astronomy, but you also have to run a business. So anyway, let me show you what you can do when you apply some mathematics modelizing the noise to retrieve the signal from the noise. This is exactly the same pictures, the same 2 images with the same 0 dB SNR, using something I name frame registration adaptive model estimation, because it's modeling the noise. And it's also a nice name, frame. So if you use this frame technique, you can do the same normalized 2D and 3D plots to see where are the peaks of correlation. 0 dB, exactly the same you saw before, where we couldn't see anything on the correlation. Now you get that. You can clearly see the peak, and you have clearly sub-pixel localization of the dx dy 30 dB by 30 by 30 pixel over here. And the only difference between what you saw before and what you see now is processing and modelizing the noise. Now, let's see what's happened if you have more than one star in the field. Here, I have an example where I have port to good SNR, 10 star with different magnitudes, still no seeing. So the SNR is stretching between 1.6 to 20 dB. And same dx dy. So you can see the star. I don't think you can see the 10 of them. Some are too dim, but you can see most of them. This is my reference image. And this is my image with my registration of 30 pixels. If you process that with the frame technique, and you look at the plots, you get this. So it's even better than before. The main reason it's better is because you have more information to process. You have 10 stars with different level of magnitude, and you can get a pretty good detection of the registration error, the peak of this correlation function, which is a statistical measurement of the probability for the two images to be offset by that much, basically. Let's see what's happened now with a poor bad SNR 10 star. So same thing, but now I'm going to use very low SNR, minus 30 dB, which is almost a factor 30 times below the noise floor, to 0 dB, which is noise floor. Those stars stretch from -4 to 0 differential magnitude versus the brightest one. So you see the brightest star over here. And the other stars are just out. You cannot see them, it's too noisy. And you still see pretty much the 30 by 30 peak location anyway. So, of course, in real life, we also have seeing, and let's see what's happened with seeing. Well, that's just a couple of slides from my old presentation on seeing. So seeing is a result of the atmosphere, who blur the image. And most of the problem coming from seeing is perturbation due to the phase of the wavefront, and that creates some wandering of the stars, which is a dominant effect. The star is moving all over the place around his average location, and some distortion of the shape, like defocus. But for most of us with our scope, we have a small diameter. The main dominant effect is just the star wanders. So one very important aspect I want to bring back here with seeing is the isoplanatic patch or angle. You see, the seeing is not identical across the field of view. It's only strongly correlated inside the tiny patch, defined as the isoplanatic angle. The idea is as soon as you have some field of view, and most of us have, at least a quarter to a half, maybe 1 degree field of view. Well, since the turbulence of the atmosphere, the eddy, are just few inch in size, in average, then the light coming from the guide star and the light coming from a nearby target, like another star, may not have much overlap at all across the atmosphere. That means they haven't seen the same turbulence. And although they may both wander the same way, they are not correlated. And at the visible wavelengths, like 550 nanometer, the average seeing isoplanatic patch, for which there is still a good correlation between the guide star, wander, and the target, is only 0.6 arc second. Not much. So we're talking about pixels. Now, of course, you can work in longer wavelengths, which is what they do in most adaptive optics out there on a professional level. And they can go above that if they go on longer wavelength, but still, it's pretty tiny. If you have a very good seeing, the eddy and the size of the turbulence is a bit larger, and you may have maybe few arc seconds now of isoplanatic angle and patch. The good news, as I said before, if you go in longer wavelengths, roughly the angle increases as lambda, a bit faster, not much though. So you're better off to go in infrared if you want to minimize seeing on at least in terms of the isoplanatic patch aspect. So This is, I think, a nice way to show the effect of that. Let's say this is a collection of stars away on the left, on the side from the guide star. And let's say I run a pretty good adaptive optics system, which is going to keep the guide star very steady. When if I look at the star nearby, I'm pretty good. But when I move away, it's blurry, and it's worse and worse, because the isoplanetic angle is now too small, and I'm out of it, and therefore there is no correlation between the seeing effect on the guide star and the seeing on that one. And if I keep going, I make stuff worse, because not only I have the seeing effect of that location in a field, but I had, in the same time, all the correction I took on this one, and since they are not correlated, then those effects add to each other instead of subtracting the effect of the seeing. So in short, you need to understand, if you want to improve the seeing, especially if you guide fast, it's useful to average information across the field. And that's what you do when you do full frame. So let's see what's happened here with a couple of examples with a fair SNR, 1 star first, under a seeing limited condition. So in this example, I have a scattered plot of the centroid for 100 samples. When I have 6 dB SNR, a factor 2, so it's a fair SNR. I use 6 dB because with 6 dB, you can use centroid calculation on a guide star. If you have 0 dB, there's no way you can use centroid techniques like you have in auto-guiding software. You just don't see the star anyway. 6 dB is probably the limit to be able to use centroid techniques. Here, the seeing, the wonder is 2 pixel RMS for the star. So now my star is over here. And if you look at the scattered plot, you see my 30 by 30 pixel registration error is spread, because in average I get 30 by 30, of course, but at every realization I have a different value because the seeing effect, the random effect of the star wander. The green dots is the result of the frame processing using the whole frame, although there is only 1 star here. The blue cross, blue cross, is a traditional centroid calculation. And you see they spread pretty much the same as you would expect. Assuming the centroid calculation is perfect, it will register the same thing, because the spread is coming from the seeing and the fact this star is wander. There is nothing you can do about it except increasing the exposure time or using a longer wavelength or a better seeing. Now, if I use the same thing under poor seeing condition, and I have now 0 dB, I just cannot compute the centroid. But I can still compute the full frame. And you can still see this pretty much the same scattered plot we saw before. See now, if we have more stars, then you can improve the situation of the seeing. And that's true if you use full frame processing or if you use a multi-star guiding. The difference, though, in multi-star guiding, you have to find those stars and apply centroid. You make assumption about the shape of them, and you compute the centroid, and you average them. And if they have the same magnitude, it's easy. If they are not, it's a bit more complex than that. But in this example, I'm just using 4 stars with same magnitude, with a fair seeing, such I can use centroid. And what we see here is the stars. That one is used for centroid calculation, for 1 star centroid, and those are used for multi-star and full frame processing. Are the results. The green dots is a full frame processing. Still, the average value is roughly 30-30, as you would expect for the dx/dy. The red diamonds are the 1 star centroid calculation, which has a spread of 2 pixel RMS, you can guess here. And the blue cross is the constellation. That's the name I use for multi-star guiding, because that's the way they name it on adaptive optic techniques, multi-star. And they spread pretty much the same than the full frame. The difference, though, is the full frame processing doesn't make any assumption about there are stars there. while a multi-star guiding, assume you find them, you have to compute the centroid of each of them. Under FAIR to poor SNR, 40 stars to show you, what's happened when you have even more stars up there. So here the SNR is between -30 to 6 dB, so most of the stars cannot be seen. Still use 6 dB to be able to compute at least the centroid of the brightest one. Same thing, the seeing is 2 pixel RMS. So that's the star I choose for guiding with a traditional centroid, and all the other are used globally when you use the frame processing. And what you get here, the red diamond is a single star, same spread we saw before, and the green dot show you a much tighter cluster for the centroid, for the calculation of the registration using the full frame, as you would expect, because all the stars were used and contribute to the process. Okay, the other things I want to talk about is with a non-axis guider, we have the capability to do also autofocus. The main reason for that, and we have a software, I think, you know by now, named Focus Lock, which use our technology known as Sharp Lock. And the idea is the light coming from your scope, the beam, is, as you know, reflected toward the imaging camera, and therefore there is no distortion. You get a nice picture for the visible wavelengths. The infrared wavelengths go through the beam splitter, and the result of, if you do some ray tracing with a very large F number here, you see quite some distortion at the focal plane of the guider, or I guess the guider sensor plane. And this is astigmatism. No, this is not at scale. It's a bit extreme, but that shows the idea. And if you look here, you can see the shape of the guide star through the beam splitter, which is basically a tilt window on the path of the light for the infrared. So at best focus, you get something like a symmetrical cross, right? You have the same amount of astigmatism in the vertical and horizontal directions. However, if you move intrafocal by, let's say, 400 microns, you get an horizontal shape. And if you move extrafocal, you get a vertical one. That means not only you know if you are out of focus, but you know where you are. And you can move the focuser as you go while you image, while the imaging camera shutter is open. Don't have to stop. It's actually auto-guiding using the on-axis guider in real time. I mean, autofocus and auto-guiding in real time. So we can do exactly the same processing globally. By processing the full frame, we can extract information about astigmatism. Instead of using one star, we use the whole frame. So I'm going now to show you that on actual bench. Before I go there, I want to say a few words about what you're going to see. I use an image I took in 1986 with my C8 orange tube and Canon. It's Ale Comet. I went to Madagascar because it was one of the best places back then to take those images. So this image was taken from a location known as Ampéfi, middle of nowhere, very, very dark, with, by the way, crocodiles, but I survived. And it was 10 minutes exposure for the one you see, and this is an actual image of the print I took back then in April 15, so not long ago, except it was 1986. So I had a C8, which was basically my guide scope, because I need a large field of view for imaging. So I had a Canon lens 200mm open at 2.8. The imager guider was a Canon F1, and the guider was me. I was guiding with the eyepiece, with illuminated eyepiece on the C8. So what I did is I took this image and I made a slide. I'm going to show you the demonstration using the slide, such we have more than one star in the field, and we can use this for the full frame guiding and focusing. So how does a optical bench look like? Well, it's basically, from a sketch point of view, it's made of, and you have seen this bench before, it's just an upgrade of it. at least some of you. There is a scope, which is a refractor. The front of the scope, there is a flat mirror. On the back of the scope, there is a focuser, is an Optec, a focuser, which has an ASCOM driver and controlled by the PC. On the back of them, this, there is an adaptive optic. It's an homemade adaptive optic. I did it long ago. We don't sell that type of things. I did it for me. But it's basically a window which is tilted by steppers. And I use it only for the purpose of creating some registration error on the image live. Therefore, we can test the focus and the guiding effect. Then you have a non-axis guider with its beam splitter. Instead of the imaging camera here, I use my slide of the Halley Comet and the light source on the back to illuminate the slide. There is a power supply which allows me to dim, change the level of signal I get from the light, from the slide. And the light coming from the slide goes back and forth. And the red one is a return path with the infrared going through the on-axis guider beam splitter to the guider, which is a ZWO ASI 1600 monochrome, uncooled. And that one is roughly 25 millimeter in diagonal. So if you look at an image of it, I took the NIAC conference not long ago. You can see the bench, the flat mirror, the refractor, the focuser, the homemade adaptive optics, the on-axis guider on the side, the zero camera on the back, and here this optical system with a slide in it, and on the back of it you can see that, but there is a light source and a power supply on the right. Okay, so me, I don't hear anybody. Hopefully you are still here.
We're still here.
Okay, just to be sure.
Yeah. It's a good time to remind anybody out there that's watching, if you have any questions, type them into chat and I'll call them out to Gaston.
Let me show you now, just before that, I will just show you the bench live, and then I go back to share my screen again. If I can go back to, where is it? Okay. So stop sharing, and you should see me, well, not me, but something like me. Let me see what I see. All right, okay. Here I'm going to show you the bench on the back. It's not very, very bright here, so you may have a tough time to see, but here what you see on the back, the imaging camera, pardon, the guider camera, the on-axis guider. Here there is the slide with the light source on the back. Here we have the Optec focuser, and then you have the scope. And if you keep going, you see on the back the mirrors, right? Just to show you, it's actually there. So now I'm going to share my screen again and do the actual demonstration. Okay, let's start with Maxime DL. You can see it?
Yep.
Okay, so that's a classic Maxime DL, and again, I use it because I have a lot of code already written for test, which is convenient for me. This will be used to actually create some error on the registration on the image. I'm just sending ST4 signal to the system, and I run my application under MATLAB. So let me clear the plots. So what you see, it's a prototype software. It's not compiled. It's running under MATLAB, so it's not very fast. The software at the end will be compiled and go probably a few frames per second. But here I log a lot of information as well. So it takes some time to read the camera with the MATLAB script. So what you can see over here is the actual registration error, which is the peak of the correlation, which is here. And in this example, everything is centered, so the error is 0, 0. There is no error at all between the reference frame and the new frames coming from the guider. And what you see here is the frame, the last frame from the guider. So you can see the comet, right? Collection of stars. And I zoom it in some aspect here to see a bit more the star in more detail. And I do that because this way you can see what's happened when I actually create some error of registration or defocus. Now, if you look carefully, you will see the star are elongated. It has nothing to do with the setup here. It's because when I took the image of the comet was moving against the star field. And in 10 minutes, I get some trail. So now we are at best focus, though we still have elongated star. And that's okay. Let's show you we don't care about the shape of what we see anyway. So here you have a lot of stars, right? And you see them here. This one is on the corner here. And the main reason I put it on the corner is when I move them a bit, this one should disappear and we can see when it comes back. So, okay, I'm going to stop now autofocus and auto guiding because I'm doing both as we speak. Clear the plot. And there is no error here, right? No registration error. Look at that star here. Because I'm going to move in array and deck, the adaptive optic is going to move the tilt and tip the window, and you see, going to start to get this star out of the frame, and we register an error here, processing the old frame again, and those are not guide stars to speak of. I just took them because they were here, and this is the brightest one anyway. An error of plus 13 and minus 11 pixel. And this star disappeared. The other ones are there. So I could pick any star anyway, if I wish here, to do auto-guiding with a classical centroid way. But I'm going to challenge a bit the system now. And you see the SNR is pretty good, 35 dB. So now I'm going to turn the power supply down, and you're going to see the star are going to fade a bit. Going to drop. So I'm going down, and slowly but surely the stars are fading. Keep going down. So you see pretty much the SNR is, let's see if I can make it close to 0. I'm close a few dBs ish, right? We can still detect the registration, but you cannot see any star. Those are not stars. Those are hot pixels. So it's no information about registration. It looks like there is nothing, but the reality is there is still information out there. But to see it, you have to process the whole frame and use some type of processing on the noise aspect, modelization of the noise. So let's start now auto-guiding. See what we get. So if I start auto-guiding, you see this is going to move eventually because now the system, and you have to give it some time because I use an aggressiveness of 0.5. The system is moving the tilt tip window of the adaptive optic, moving back the scope on track as it should be. So it's pretty much like controlling the mount if you would do that. We are almost there, almost. The error is now quite small, below a pixel. Processing only that, right? So you couldn't do any centroid calculation with the guide star. There is no guide star to see anyway. And now if I turn the light on, you will see everything is at the location it should have been. You see my star here is back where it should be. Everything went back to the right position, so guiding worked. And as I said before, we can also do autofocus. So now what I'm going to do is moving the focuser here in order to create some level of defocus. And see, and by the way, I'm going to move the focuser by a lot. So the result is we'll get some registration error on the image, and the auto-guiding software, which is still running, is going to correct as we go. When you use real-time autofocus in real application, you never move the focuser by that much. few microns at a time, so you don't see those errors. But here I'm going to move by a few hundred steps, so it's going to create some error because the mechanic is not perfect. But my goal is to show you the defocus and the autofocus eventually. So look at the shape of the star here and there. They're going to be blurred. You see, they become quite blurred and elongated that way. And we have some registration error because the motion of the focuser is not perfectly on axis. And that's just, microns, but we can see them. So the system is correcting as we go. And now if I start the autofocus here, now the system is going to do autofocus and auto-guiding full frame. And you will probably see some effect of moving the focuser back, right, on here, on the guiding. Same thing, so the shape comes back to best focus, and the image becomes much better, sharper. And now we are back in business with guiding and focusing full frame. As you saw, we can guide and do all of that with pretty much almost nothing to see on the image. Yet, there is still some information. The point is, if there is nothing, nobody can do anything anyway. But if there is some information, some pattern on your image, even if you don't see them, we can process it and retrieve this information every few seconds here. That's it for me. I guess if you have any question, I need to put my camera back. And stop sharing.
You got it.
You see me?
Yep, we see you.
Okay.
The one question you're getting is how much back focus does the on-axis guider add?
We have two models. The one for the smaller camera, APS-C size, and the bigger one, full frame and above. The first one is 66 millimeters. The second one is 68 millimeters. It's pretty much the same.
Okay. And to take advantage, I should actually rephrase that. Everything you had demonstrated basically applies only to the off-axis guider, but if you're, excuse me, the on-axis guider. But if you're using the on-axis guider, then you get to really take advantage of that, both focus lock and multi-star guiding. Because it would the full frame guiding, it probably wouldn't work so well if you were using an off-axis guider, correct?
Yeah, well, I guess you can use only one star and do the same thing, right?
Mm.
It doesn't matter what you have, so it could be a star or an alien spaceship. But if you have a small field of view, then you may be limited to how much information is there and how much SNR you can actually extract from it. So it would work with an off-axis guider, but the field of view at once is pretty tiny.
Right.
Off-axis guider, you can rotate, but you don't have the field of view at once, So you cannot rotate while you image. If you use a guide scope, I guess it's a better option, but you lose the autofocus capability.
Mm-hmm. Yeah, and having that on-axis guiding gets, I'll say, a more accurate read on the how the seeing error is distributed through the frame.
That's right. You see the same frame pretty much. Then your imaging camera, a lot of overlaps between them. And today, if you consider the price of those zero camera, to take an example, they are pretty much the price of what used to be a small chip auto guiding good camera. So why to stop and use a small chip when you can use a way bigger chip and use those type of techniques? Now, you can do the same thing today if you have an on-axis guider and just use centroid techniques. On the one, because with a large field of view, you have a quite higher probability to at once to get guide star, and those software like PhD or MaximDL or other will just work fine, but they will work with one star or few star if you use MaximDL, I guess, has a multi-star capability. But you don't process the whole frame to speak of. You use the fact you have access to a lot of information, but you still process one star at a time. Here we process the whole frame.
Mhm. And so the issue with one-star guiding is the seeing causes it to get erroneous, or an erroneous centroid, I guess you'll say, or maybe the erroneous location of the centroid. So you're cutting down on that erroneous location, and as your plot demonstrated, you're not sending or having to deal with what I'll call erroneous corrections to your mount. Like we use hysteresis and all of that stuff to say, well, I know the star's jumping around. I don't want it to be that aggressive, but you're getting a better, more accurate location of the star throughout the frame.
Yeah, having said that, it's all about, how fast you want to guide. Because if you guide with long exposure, and I always tell people, don't rush guiding unless you have to. Because most of the time with the mounts we have today, we have slow drift and pack capabilities. So you don't have to run every second. Because if you do that, first it becomes more difficult to find a guide star if you use classical centroid. On top of that, you're going to chase the scene. So if you have few seconds, 5, 10 seconds, you can afford that. I think it's a win-win situation, and seeing becomes very, very little. So, but the interesting aspect of full frame is if you want to go fast, you have a better result with seeing, because you have it's not like, when the star wander is, the centroid you get is for that star, but the other piece of the image is distorted another way by the seeing. So there is no such unique actual centroid. Everything is blurred. So my advice is either you go slower and you expose longer, or you may go faster but use maybe a full frame, or go in longer wavelengths like infrared, where you have a bit less seeing first, and also a larger isoplanatic patch.
Great. Now, a few questions popping up. Alex is asking, how does this work at the imaging session? So, for instance, can he just tell SGP or Maxim or whichever program to use your software and off it goes, or is your software standalone that goes on top of Maxim? How does that work?
Well, that's a fair question. We are still working on that. I think there will be a couple of things. The first things I hope to have by the October for the Advanced Imaging Conference at San Jose is a standalone application, a bit like SharpLock and FocusLock you have from Optec, who do that under license with us. Is going to talk with most of those common software like the SkyX, the Sequence Generator Pro, and MaximDL and PhD, and taking data image from the guider and control the focuser and for autofocus and the mount. Therefore, as long as both software can talk, and is what we already do with FocusLock, then that software will work with your imaging software, but will be responsible for guiding and focusing live. Now, I've been approached by the folks from the SkyX, ACP as well, to see if we can implement this technology directly native on those softwares. And for ACP would be something probably on MaximDL, because they use that as the main engine. I don't know yet. My hope is if we can implement native, it's even better for everybody. But there is still some discussion to go there and negotiation. So that may be a bit the next step, taking a bit longer. I think to provide solution like that to everybody, I'll go first with this standalone solution, and then we'll hopefully get more traction and integrate that in PhD and other software down the road.
Great. Max is asking, any chance there will be an off-axis option? And I don't know if he's referring to the full frame or the focus lock, so maybe just speak to both of them if you could.
Sure. First, if you think about autofocus with one star, right? You already have the capability to do that with an off-axis guider if you buy the kit for a Lodestar from Optec. They have a kit named Locerta, I think. who create the astigmatism you need to work with focus lock with an off-axis guider. Of course, you have to find a guide star, and it's going to work with one star. That's one aspect. Otherwise, I mean, if you think about that software, this technology, the frame technology, as I said before, it will work with one star if you have only one star coming from an off-axis guider or a self-guided camera. However, you lose the capability unless you have this Lacerta device or the on-axis guider to do the autofocus, because we don't have information about focus direction to control the focuser.
Okay. I think we answered. Excuse me. I think we answered Isaac's question. Does the guiding software work with the SkyX as well as Maxim, or only with Maxim? But I think you answered that a little bit. But why not tell us, is the software available now, or is it going to, when is it going to be released?
Well, there will be a beta version for Maxim DL first. I have a few people interested to work on that. And the main reason I do that is because I already have all the pieces to do so. There's nothing specific with Maxim DL, it's just the way I designed those stuff long ago, and so try to reuse what I have. But that's a beta one. Now, the software for October this year, for the Advanced Imaging Conference, will be like Focus Lock a bit. And it will work for several platforms, cross-platform. We expect to have the SkyX, Sequence Generator Pro, Maxim DL, and PhD2. Well, actually, PhD2, we don't need it because it does only guiding. But I mean, the SkyX, Maxim DL, and Sequence Pro generator, that will be the goal.
Okay. Ignoring differential flexure, how well would full frame guiding work with a separate guide scope that's well aligned with the imaging scope?
I think it will work well because it can do pretty good tracking with very low SNR. So I think that will be also true with a guide scope, though often you have maybe less limitation because you have a large field of view. But it will work. It doesn't matter from where the image came from. But you will lose the autofocus capability, though. Right. Because even if you would have a way to create astigmatism or something similar we use here, you wouldn't have information about the focus of the main scope.
Mm-hmm. Basil's asking, how are hot pixels or cosmic ray hits handled?
Well, I don't want to go to the specific, but yeah, we do pre-processing of the image to remove them first. Because when you do modelization of the noise and you want to use those optimal filtering techniques, you need to remove those artifacts first. They are outliers, basically. So there are a couple of layers of processing here. And at the very basic level, those artifacts are removed. And by the way, what you saw today was using any type of dark frame. I didn't use any dark frame to calibrate my guider. I guess we could add this option, but I designed it such we are immune against hot pixels and artifacts like gamma rays, because those may happen anytime. And using a dark frame is nice to have, but if we work without it, is even better.
Okay, I'm not sure I understand Isaac's question. When you say full frame, is that a 35mm diagonal detector? And
No, it's full frame. By that I mean the whole image from the guider, whatever the size of the guider may be. Right. I use all the frame.
Right.
So the one you saw here on the demonstration was ASI 1600 from Zio, and this one is a 25mm in diagonal, which is close to DSLR size.
Right.
But any size will work.
Yeah. Yeah. So you're not speaking to the size. You're just speaking to the guiding stars are taken from the entire visible frame.
Right. And you see, you can guide on most likely on your frame, on your guider, you will have some stars. You may not see them, but they are likely to be there, very beneath the noise floor. However, if you don't have star, you have probably something else, like a galaxy or some pattern. And you saw the image of the moon landing. We just don't care about the shape. We care about the fact there is something, and we can extract it from the noise because we can modelize the noise. And the good news in astronomical images, sensor and noise-wise, it's pretty easy to modelize. The noise is something pretty simple, if I can say so, statistically speaking. There are some fixed patterns problem like that, hot pixel, you have to be careful about being robust. But if you have a good assumption about the noise, then anything not above, but anything else than the noise will be used for the calculation. And so you don't truly need a star to speak up, you need something else than noise.
Okay. Alex is saying he can see a standalone application to control guiding and focusing at the same time, full time. Will that standalone software be able to dither? So I guess he's asking, is your,
yes.
Are you dither capable?
Yeah, because we can always tell the system to change its target between frames. The way it works is when it talks to software like MaximDL or the SkyX, to take examples, we get access to the COM server about access to information about what's going on and when a frame is over from the imaging camera, and when we get a new one, which filter is used. So we can deter by knowing the next frame should be deterred by some random value. And the way we'll do it is we just decide, and we add some random error on the registration value, which is not 0, target, but maybe +1, -3, or whatever this deter strategy may be.
Okay. His next question is, the on-axis guider works with the lodestar or any other guider? And I guess in general, the question.
Or any guider.
Yeah.
I mean, if you use a lodestar, you're going to have a small field of view at once. Mm-hmm. Now, the product was designed with a stage, an XY stage. Such, if you have those type of camera, because they used to be very popular, and they are still, I guess, you can explore by moving the stage manually, the whole field of view, even if you have a small chip, like you rotate an off-axis guider, I guess. Mm-hmm. But you cannot get everything at once, because you have to move something. Now, over the years, we got more and more people going remote and robotic. And I was asked many times to motorize the stage, and I told them, I don't think that's the right thing to do. You're better off to use a bigger chip and move nothing. And it's cheaper because moving the stage, it's a quite difficult mechanic to be accurate. It's expensive. And now today you pay, I mean, the 25mm diagonal zero camera, I think is below $1,000 now. And I was just at NIF, NIAC, so, and the next booth was zero focus, by accident, I guess. And I think they have a new one. I forget which one. We have a little bit 22mm diagonal, but for something like $600. Mm-hmm. So you can, the on-axis guider can take any guider you want, but my advice, if you start from scratch, I would suggest to shoot for a large chip because they don't cost more than today's guiders.
Right, and really, having the on-axis in infrared, how important is sensitivity of the guide camera? Do you need the sensitivity of a lodestar?
Well, the answer is yes and no, because if you go with full frame techniques like you saw, we can work with very low SNR, so it's less sensitive, less an issue than you maybe used to be. Now, first, you need to understand the camera must see infrared. So if you have a color camera or one-shot color with an infrared filter in front of it, it's not going to work very well. So you need a monochrome camera without any filter now. Those cameras use CMOS or CCD. Today it's more CMOS. And they are quite sensitive in infrared up to at least 1,000 nanometer and quantum efficiency is better and better because they have also application for night vision security camera. And this is, if you go to our website under, I think, education page, there is also a menu. On the menu, there is something about guiding in infrared, and you will see some maps of the sky and how much impact guiding infrared may have on limiting magnitude for the guide star. It's not as bad as it seems, because a lot of stars have a lot of infrared radiation. But of course, you lose everything below 750. So far, it works pretty well, even with one star. It will work way better with frame techniques, because it just work with very, very low SNR, where you couldn't use guide star anyway.
Right.
Adam, I wrote a question here. Do you understand what I'm asking?
I saw it pop up really quickly. I just got another question emailed to me. So I'm going to read out this question and then read your question right after. Gaston, can this be combined with adaptive optics to get even better results?
Well, the short answer is yes. You can use it with adaptive optic if we write the software to do so. And some of adaptive optic, is proprietary software. I mean, so we'll have to discuss with Speak, for instance. So that would be just a technical and commercial aspect. There is no limitation there. Now, having said that, do we get a better result? I think you will average better the seeing across the field of view, but if you expect to use adaptive optic to decrease the seeing on your image, it's still a challenge, in my opinion, unless your seeing is mainly coming from very near ground boundary effect. You're going to have a problem with field of view like a half degree. Now, if you have a problem with the mount, of course, I mean, the mount is not perfect, since all the error is correlated across the field, yes, and you will minimize the seeing on the adaptive optic in that case, that's for sure.
Okay. I'm reading Eric's question. With the S-Big cameras and their filter wheel with the built-in guider, you move the pick-off mirror so it's just on the edge of the frame. With an 11002 chip, it's rectangular. The guider image is actually in the field of view. That is, the guider image is in a similar position as the long axis of the primary image. Therefore, you should be able to use your system to guide with stars that are in what would be a square field of view. I'm not sure I understand that, Eric. I don't know if Gaston did.
Well, basically, Gaston, when you describe having the off-axis guider outside of the field of view and the problem that occurs, but with a chip that's like a 35 millimeter, and if you put your pick-off mirror on the long side of the chip, which is where it is in those guiders, basically you're almost within the field of view if you consider it like an 802 chip, and therefore you wouldn't have a lot of the problems of a guider which is way off of your field of view. You essentially would be guiding, if you could put your software in there, from stars that are in the edge of the field of view, the image circle.
Yeah.
Well, I think you're right. I mean, of course, you are still off-axis somewhere if you define off-axis being outside of the imaging camera field of view. But of course, you are more or less off-axis depending which, if it's not a rectangular, a square sensor. As I said before, I mean, if you go off-axis one way or another, or on-axis, whatever, this system will work in any configuration, even if you use a self-guided camera, for instance, or the one you are talking about with a filter wheel and the pickup front of it, it will work. Of course, you have a small field of view, so you will have less information to get from the image, and then you get what you get. My point would be, if there is no guide star there, you couldn't guide anyway with a classic centroid, and you may have a hope to guide with this, because there may be still information you could retrieve, although you don't see it.
Well, the reason I brought that up, Gaston, is because with the long focal length telescopes, you don't have many stars to guide in, and rotation angle is important. But with your wide field of view, like the 130, there are dozens of stars in that pick-off mirror.
Well, in that case, it will work just fine. Well, you don't have the, though you lose the autofocus capability, but
Yes.
Now keep in mind though, and that's maybe a detail, but when you go off axis with guiding, and when you go more and more off axis, you may start to see some field rotation if you are too far off axis and your polar alignment is not good enough. But in most applications, that's not a big deal, because we can always take care of that by post-processing, and maybe the polar alignment is not too bad. But we need to be aware of that. The best way to minimize rotation is to be as much on axis as you can.
A good question coming from chat. If your on-axis guider guides on infrared light, it has a pick-off prism. If you plan on capturing in near infrared, would you not be able to use the on-axis guider?
The answer is yes. We have a couple of customers, not many though, who wants to image in infrared. And so most of them were for science. Mm-hmm. And what they do is we offer an astigmatism corrector for the guider port, which is designed to correct the astigmatism. Of course, you lose the autofocus capability, but in that case, you guide from the visible port and you image from the infrared one, from the guider. You just reverse the system. So we have a couple of people doing so, and we have even a custom version with a different dichroic mirror used in Hawaii now for some research in young stars, and they needed a different cutoff wavelengths, and they image through the guider and guide through the imager.
That makes sense. I'm sorry, I'm just reading through these. Okay, yeah, I think it was more intended for chat, just speaking to the number of stars available in an off-axis guider. But and I'm reading in our internal chat now, but I think we've pretty much got most of the questions covered. Gaston, I do want to thank you. First of all, I'll say if you guys have any other questions, feel free to type them in. If you want to check out Gaston's products, innovationsforesight.com, I believe it is.
Yes.
And you can read basically all about the on-axis guider. It's interesting that it first came out, what was it, 5 years ago?
Yeah, about that time.
And a few people bought them, but I think right now you're actually unlocking the real capabilities of it by using the focus lock and now this full frame guiding. Seems really interesting where it's going.
I think also, something changed since is those large camera cost less and less.
Yeah.
And I think the price will continue to go down, most likely. So I think we'll have more and more opportunity, and with the on-axis guider, you enable the system to use those cameras, and everything goes together. I'm not on the camera market, but I'm pleased to see those cameras at that lower cost now, because it changed the game.
Yeah, absolutely. It's definitely it's gonna be in a different place in a couple of years from now, which is what's interesting. Yeah. Is even a lot of the camera manufacturers I spoke to that have already introduced CMOSs are really excited about what's coming up. So,
well, I think CMOS is a way to go anyway. They're going to drop CCD in down the road, except few. But I talked with the guy, the owner of Zero, because he was near, next to my booth, and he's a very young, bright guy, very motivated, who knows the business, but also the technology. And they come with new product all the time. They are not in the market since a long time, but they have done a long way anyway. And they want to come with more sophisticated product, bigger camera with filter wheel, bigger things. And I think they're going to have a big impact on the market for good for us customer, because they have a very low price point.
Absolutely. Yeah, Lou, I think you're getting your answer there. Don't put your H-alpha filter in front of the guider if you can avoid it.
No, but normally you shouldn't have to do so, because the whole idea is the filter wheel needs to be close to the imaging camera anyway. Otherwise, you have vignetting problem with the filter, and therefore both of them go on the imaging port on the axis guider on top of it. So it's never in front of the guider. Think about it like a, basically a star diagonal, right?
Yep. Okay. I think we got pretty much everything, all the questions covered. So again, Gaston, thank you for coming on. You can check out his products on his website, become a customer of his, and I don't know, hopefully he'll be on in the future to discuss some other things. I do want to say one thing. One of the most interesting, and it applies to what we had heard here, one of the most interesting presentations we've had on the Astro Imaging channel was Gaston's presentation on seeing, which really goes a long way to explaining what's actually going on in regards to how much it jiggles and how different it is across the field. It's a little bit in depth when it comes to the math, but it was also enough that even someone who's not extremely proficient with the math would get a good understanding of what's going on. And if you're looking for a catch up on that, it's definitely worth watching. I've watched it more than once just to kind of see what I could learn just by watching.
Well, if you are lucky enough to come at the Advanced Imaging Conference in October, I'm going to give a couple of workshops on that topic too.
Okay, and that is,
I'll be a speaker.
That's California, right?
That's right, San Jose.
San Jose. Great.
There is a worse place to be.
Yeah. In October, for you and me, it'd be nice to I don't know, have like a January or a February in California.
Yeah.
But I guess October will do. Finally, some good weather here. Not clear skies, but good weather here in Northeast PA for me. But again, thank you, Gaston. Next week's presentation, Warren Keller and I forget his partner's name, Peter Prelou, I believe it is. Warren will be on to go over his new subscription service to his IP for AP, his video series on learning whether it's Photoshop, PixInsight, or there may be some other programs in there. And also to probably tell us a little bit about his new book. But either way, he'll be on next week, and should be a good show. Thanks again to everyone for watching, and thanks again to Gaston. And I believe we're going to end it for tonight, but I will see all of you guys next week. Have a good night.
Thanks, Adam.